Webcast is now starting. All attendees are in listen-only mode.
Good afternoon and welcome everybody to the IGHG webinar, the COST Cap project and overall results. My name is Mónica Garcia and I will be chairing this webinar. I'm technology analyst at IGHG and I'm here together with Susanne Killick, events manager at IGHG. Before proceeding, I would like to show you a disclaimer from IGHG. We are part of the Technology Collaboration Program, and we are part of the International Energy Agency Energy Technology Network. So the information I'm going to present doesn't have to be in total agreement with our members or IEA Secretary. So this slide shows you our members, and we would like to thank our members who set up the IGHG strategy and support us in our work. Said that, I would like to introduce you our core activities. So first, we assess mitigation options. We focus on our R&D on CCS. We track capture technology, development and costs. We monitor geological storage performance, and we provide our members policy audience with independent technical input. Said that, I would like to remind you all that we will have 4 speakers today who will give an overview of the final results of the COST Cap project. This was a Norwegian-Swedish research initiative carried out from 2015 to 2019 and aiming to reduce the cost of carbon capture in process industry by developing concepts for partial capture. Today, each presentation will have a duration of 10 minutes. First, Ragnhild Skakestad from SINTEF Industry will present the COST Cap project and overall results. Then, Max Bjerman from Chalmers University will present the scenario from near-term implementation of partial capture from blast furnace gases in Swedish steel industry. And then Annette Mathisen from SINTEF Industry will present CO2 capture opportunities in the Norwegian silicon industry. Finally, Jens Wolf from Rice Bioeconomy will present the partial capture of CO2 from a pulp mill with focus on cost reduction. At the end of the session, we will have 15 minutes for a questions and answers session. So please submit your questions during the entire webinar, and we will try to go through all the questions at the end. It's possible that we will not have time enough to cover all the questions, and in such case, we will try to come back to you later by email. And with that, we would like to transfer the connection to our first speaker, Ragnhild Skakestad.
Thank you for your kind introduction, and good afternoon to all of you. Today I will present the COST Cap project, which is a short name for cutting cost of CO2 capture in the process industry. The project has been a consortium with several partners. I would like to thank the COST Cap industry partners SSAB, Elkem, Norcem Brevik and Argagas, and the research partners SINTEF, Chalmers, Rice, Sverige and University of Southeastern Norway. I would also like to thank the Global CCS Institute and EAA GHG for participating in the project and giving us the opportunity to do this webinar. The project is funded by the Norwegian Climate Demo Program via Gassnova, the Swedish Energy Agency and participating industry and research partners. So, COST Cap is a Norwegian-Swedish research project started in 2015 to investigate how to reduce the cost of CO2 capture in the process industry by developing concepts for partial capture. The project is based on the following. Carbon capture and storage can be implemented at large scale. It is commercially available and is one of the techniques required to reduce global emissions. But the cost is still high compared to the ETS market price, so implementation of CCS has gone slowly. This project has been running for 4 years, so it is finalized this summer. We have had 4 PhD candidates working on this project and over 15 papers and several presentations at conferences. We have a web page where you can find more information of the project. So, the overall aim of the COST Cap is to suggest cost-efficient capture strategy for future CCS system for different industry sites, and we have considered different approaches. We have utilization of waste heat, at more efficient use of biomass resources. We looked at different capture technologies and optimizations there, and see how changes in the market condition may affect the capture costs. We have also investigated if and how much partial capture could reduce the capture cost for the industry. But first, to define partial capture, it's necessary to first define full capture. What we in this work define as full capture is the highest CO2 capture rate technically feasible with correspond to capture rates above 90% from a CO2-rich gas. If you apply it to a coal-fired power plant with access to heat from a steam cycle, a high capture rate will usually also lower the specific capture cost and be beneficial to the plant owner. So many studies on CCS in process industry commonly tie a capture rate of 90%. But however, in many industries, depending on condition of the CO2 source and the energy system at site, a high capture rate may imply excessive costs that increase even the specific capture cost. So we in this project define partial capture as a carbon capture concept where only a share of the accessible CO2 from a flue gas or process gas is captured, with the extent of this share being governed by economic factors such as energy price or policy-driven requirements. If we have a look at the figure here, it shows the carbon flow of a pulp mill. There are several different CO2 streams, and capturing all of them would require a really high cost. Distance between them, differences in impurities, and concentration would make it very expensive. In addition, carbon capture is also very energy demanding. Many industry sources do have some waste heat available. How much CO2 can we capture with that amount? This project had focused on capture rate and finding the best level for this for different industries. The following example illustrates in which scenario partial capture may be preferred over the full capture. Plants that have an energy system that constantly or depending on market condition may produce a part of the heat needed for carbon capture at low cost. Plants that are regulated by emission performance standards require lower capture rates than full capture. Plants that would like to reduce investment risk in CCS deployment due to lower investment cost than full capture. And for plants with multiple stack, targeting the most suitable stack instead of a total site emission. And last, plants where carbon capture is cost efficient in a combination with other mitigation measures. So, the stCap project focuses in 4 industries that have process-related emission of CO2. That is, emission are not only from heat supply, but also part of the manufacturing process. Such emissions are likely to require CCS, as they are difficult to reduce by measures like fuel shift or electrification or energy efficiency improvements. We have been focused on 4 industries, in iron and steel, in cement and silicon, and pulp and paper. We will later describe 3 of these cases more closely. So this showed the methodology in the stCap project. We started with different energy system scenarios. We looked at case and site-specific plant data, and then we used all of these to do process simulation and cost estimation for the capture process. We focused in waste heat available, cost of steam, CO2 concentrations and volumes, and we investigated several scenarios for each case. And then finally, we find a cost-efficient design and good way to implement partial capture for an industry site. And then I would just say some quick word of the cost estimation tool we have used. The tool is owned by Syntef Industry and is based on early phase cost estimation. The accuracy here is quite low, but it's fast and suitable way to compare different scenarios. We use detailed factor estimation method, and it's based on simulations from ASPEM. The equipment costs are from databases or from industry, and the result gives installed cost in total and for each cost element based on equipment cost, choice of material, plant type, etc. It's a strong tool when you do benchmarking, comparing different cases with each other, and it's also viable to do the sensitivity to see how changes in one parameter would affect the total install cost. So, this is an overview of the 4 different industry cases. We have looked at cement production at Norcem Brevik in Norway, which is located at the red star. We looked at pulp production at a generic pulp mill in Sweden, that is the green star. And the silicon production at REC Solar in Kristiansand in Norway, which is the yellow star. And finally, the steel production at SSAB in Luleå, Sweden, and that is located at the purple star. So this is a short introduction of the cases. We will go in detail later in the webinar. We have focused on available energy and steam, and we have looked at retrofit cases. We are mainly focused on MEA capture technology, but we have also some oxy-fuel cases. We have looked at large differences in size from 50,000 tons CO2 up to near 2,600 kilotons CO2 per year, and large differences in the concentration from 1 volume percent to 30 volume percent CO2. It's also important to know that some of the scenarios utilize available energy for production of green electricity and district heating. So, to the results. This figure shows some of the results from the project. It has capture cost on the y-axis and the full capture or partial capture cases on the x-axis. The silicon case sticking out, and that is due to the fact that the silicon plant we were investigating had enough steam to capture 90% of this CO2 emission. If you focus on the steel, pulp and cement cases, you can see that for all of them, partial capture reduces the capture cost significantly. You can also see that there are large differences in the cost of steam, and that have a major effect on the operational cost. So, summing up, partial capture is a solution to reduce the cost of CO2 capture if the sources have several stacks or emission points, or if they need to reach a certain level of CO2 emission to meet emission regulations. It's also viable if the plant have access to low-cost energy to cover part of the energy demand, and if they can vary their product portfolio depending on market condition, or have large differences in base load and max load. You can find more information about the project at our web page. And by then, I want to thank you for your attention. And now we will have more details from the case study. So I will start giving the floor to Max Biermann, who will present the steel case.
Yeah, thank you very much, Ragnhild, and thank you, Monica. Before I start, I would like to thank the people at Swerim, SSAB, SINTEF, and USN working on the steel case with me and my supervisors here at Chalmers. I will give you an overview now on the results from the steel case and try to paint the bigger picture of a possible near-term implementation of partial capture in the steel industry. First of all, I want to give you an overview of steelmaking, so we're all on the same page. Roughly 70% of the global steel is produced by primary steelmaking, so that's from scratch, so you use iron ore, mined iron ore, and the remaining 30% is, roughly speaking, secondary steel making, which is predominantly using scrap steel. The vast majority of primary steel is produced in so-called integrated steelworks, which I've marked out here for you, where the iron ore is reduced with coke and coal in a blast furnace before converted to steel in a basic oxygen furnace, which you see down here below, BOF. Yeah, then you refine it to the alloy you desire. Compared to secondary steel, to primary steelmaking, secondary steelmaking is less energy and less carbon intensive, and is estimated to expand its share in the 21st century. But we will need to reduce primary, to decarbonize primary steelmaking to achieve our emission targets in the EU. For this, the steelmakers have, 5 steelmakers, at least in Europe, have introduced a concept called hydrogen direct reduction, where you basically reduce the iron ore with green hydrogen, one from renewable electricity through electrolysis. And then this direct reduced iron is melted in a shaft furnace, an electric arc furnace, sorry. All right, so the question is, how does CCS fit in? Here we see in the graph the emission intensity of steel in ton CO2 per ton steel. And we have the integrated steel mill and the hydrogen direct reduction. So this shift will happen in 2040, 2050, estimated. And the question here is, how does CCS fit in, and does the steel industry continue its business as usual until this technology is ready, or could CCS play a role before? And in that case, what techno-economic conditions for CCS are needed? I will, before I answer that question, I will just briefly show you some highlights of the methods that we've used. To the left here, you see the flow sheet of the process, the MEA process. What is special here is we've been using a rich solvent splitting in all cases, actually, and in the steel case, we also added an intercooled absorber, ICA here abbreviated, because of the high CO2 concentrations that we have. And then we also enter the absorber. We enter the entire gas flow of a CO2 source, and then we lower the liquid to gas ratio to obtain CO2 separation rates below 90%, and that lowers the specific heat demand in the stripper, so we can be more energy efficient. And to the right here we see economic parameters, and I've highlighted 3, which I think are maybe special to the case. The steel case, we have a very high plant availability due to the steel units having quite high availability of 98% or even higher, and the electricity cost is rather low due to low cost of electricity in northern Sweden. And what is special here, and what's also special to the project, maybe, that we've assessed the steam cost separately. So we've done a bottom-up approach in assessing the value of excess heat. All right, the Luleå steel mill basically has 3 CO2 sources that we looked into. 2 of them are atmospheric; they're end of pipe. So those are flue gases, the hot stove flue gas and the CHP plant flue gas, which we see here to the right in the picture. This is a carbon balance, by the way, I forgot to say that. So these have high concentrations of atmospheric pressure, and the blast furnace gas in the middle, which you see here, is a process gas that is used for heating purposes and throughout the site. It has also high CO2 concentration, but a slightly higher pressure. We jump directly into the emission costs. The emission reductions and the capture costs we see in euros per ton CO2 captured on the y-axis, and on the x-axis we see the amount of captured CO2 in million tons per year. And just as a quick explanation why the graphs runs like it is, we see here this is the economy of scale effect in all these curves when we go down in cost with increasing capture. And then every time we see a step here, we see that that's an investment cost into the next heat retrieving technology. What we can see from this graph is that we have a region of lowest capture cost, and this is between 20 and 38% capture of the site emissions. And this, from the 3 investigated CO2 sources, we see that the blast furnace gas is the CO2 source which has lowest capture cost. If we compare this to the full capture case, which is 90% capture from the blast furnace gas, the hot stoves, and the CHP plant, capturing 76% of the CO2 site emissions, we see that partial capture with excess heat and back pressure from the CHP plant, back pressure steam from the CHP plant, this partial capture is more cost effective than the full capture case, which relies on the combustion of extra fuel. Here I've also listed the excess heat sources. Those are more described in the papers and the publications if you're interested. We can also have a look at the capture cost structure. So we can see for partial capture here to the right, That's the left bar here in the right diagram. That partial capture is dominated by capex, and less so by the steam cost. And this observation is different for full capture, where the steam costs dominate the entire cost. And since the steam cost here is the large part here is the fuel price, which you have to pay to obtain your fuel, and that could mean that you're more exposed to a volatile market, for example. So this might be something to consider when making investment decisions. The production cost, if we push on the cost of the capture cost onto the steel that is produced, we increase production costs for steel by 4 to 17% for the investigated cases. Talking about near-term implementation, so when can we actually do this? So I've tried to compare the full capture cost and the partial capture cost, and this is now full chain cost, so we include transport and storage, assuming ship transport. So if we compare these to CO2 prices, we of course are compared to today's prices of roughly 26 euros per ton CO2 in the EU. We are too low, but if there would be policies in place that value carbon at a price of 40 to 60 euros per ton CO2, we could implement partial capture. So in the plot here we see WEO 2 degrees C. That is a sustainable development scenario by the World Energy Outlook 2018 for advanced economies, and the EU ETS forecast is by Refinitiv. Yeah, so there's a window of opportunity here. That's one key takeaway. We have to implement partial capture in the coming 5 to 15 years. Afterwards, the time is too short, the economic lifetime of such a unit of roughly 25 years, what we're calculating with. That would be too short before we would need 100% emission reduction with either full capture or with other low carbon technologies. Now, if we look at the question I had in the beginning, how does CCS fit into the picture when the steelmakers are already talking about this hydrogen direct reduction, going from business as usual down to hydrogen direct reduction? Well, if we put in the red curve now, which is partial capture, we see that 80 million tons of CO2 can be captured before, and these accumulated emissions are relevant. These are the relevant emissions we have to start mitigating as soon as possible. Partial capture could therefore also de-risk the late arrival of HDR, and we can see also that to the right here, below zero, we can capture some of the CO2 that is biogenic in these HDR concepts. Alternatively, we could also capture CO2 from hydrogen production from fossil fuels. So if we have the infrastructure in place, we could do SMR, for example, or others. Then partial capture could evolve towards full capture, using biomass potentially, and also solvent improvement. So there's a potential to even capture more with other mitigation options or with improved technology. So to summarize the key findings here, for integrated steel mills, partial capture powered by excess heat is more cost efficient than full capture relying on external energy. The near implementation is possible if we have the right policies in place, valuing carbon at 40 to 60 euros, and there's a window of opportunity we may not want to miss. And there are synergies with other mitigation options, and there's possibly a synergy also in the transition to hydrogen direct reduction for the steel industry. Thank you very much. I will now give the word to Annette Mattisson at Sintef, who'll talk about the silicon industry.
Thank you, Max. So this part concerns CO2 capture opportunities in the Norwegian silicon industry. And I would very much like to acknowledge the cooperation with Elkem for this work. So seems to be some problem here. Let's see. I'm not sure. Can you see my good son?
Yes, we can see your screen.
Okay, because it didn't change on my side. Sorry.
You have control in it, so just press the page down. It should just move on because it's on your laptop.
Yeah.
Okay, now it's working. Because
Yeah.
it just, sorry, but it just moved something here.
Yeah.
Okay, so again, first briefly about the industry in general. Silicon production is an energy intensive industry, and both electricity and carbon-based raw materials are consumed in the production process. Norwegian silicon has one of the lowest CO2 emissions per ton product. This is mainly due to process efficiency and hydro-based electricity. Still, pathways are explored to reduce emissions, and other than CCS, the focus is on process development, waste heat utilization, and bio-based carbon sources. So the first plant chosen to represent the silicon industry in the project was a small silicon metal plant. However, as it turned out to be challenging regarding CO2 capture, a second plant was included, and this was a ferrosilicon alloy plant. Although they produce different silicon materials, they have to a large degree the same production process, where the main part of the process is an electric arc furnace, where quartz is reduced by carbon via the reaction shown. With the current process, all the CO is oxidized above the charge level to CO2, and the off-gas leaves the furnace at between 400 and 700 degrees Celsius, which means that there is residual energy available. And therefore, energy recovery is installed at some, but not all plants today. So the first plant was REC Solar, located in Kristiansand in the southern part of Norway. Typical production is 10 kiloton silicon metals from one furnace for use in solar panels. The corresponding CO2 emission was 43 kiloton from fossil and 12 kiloton from bio-based sources. The plant does not utilize waste heat today. With 55 kiloton CO2 annually, this is a small plant, and as we shall see, it also has a low CO2 concentration in the off-gas. The schematic overview of the production process, shown at top of the slide, shows that carbon and quartz enter the furnace, liquid silicon metal is produced, the off-gas leaving the furnace is cooled and passed through a filter. In the filter, microsilica is recovered as a valuable byproduct, and the particle-free off-gas leaves through the top of the filter. Two streams have been highlighted. These are stream 7, the off-gas leaving the filter, and stream 4, the off-gas leaving the furnace. Stream 7 was the primary focus, as this is the stream leaving the filter. However, as it seems from the table, it only has a CO2 concentration of 1 volume%. Therefore, stream 4 with a CO2 concentration of 3.7 was included in the investigation. And here it was assumed that it would be possible, if the filter design is changed, to maintain 3.7 volume% also after the filter. And the plant has sufficient excess energy to capture 90% of the CO2 produced. So as mentioned on the last slide, two CO2 concentrations were investigated. Additionally, as the plant was small, only 55 kiloton CO2, an increase in size 3 and 5 times was included. And based on these 3 scenarios were developed. Here the first two, 1A and 1B, represent 1 volume% in the off-gas, where 1A is the reference case, where an electric boiler provides steam to the stripper reboiler, and 1B where steam is generated by the excess energy in a waste heat steam generator. Scenario 1C represents 3.7 volume% CO2 in the off-gas, and again with steam from waste heat steam generator. So the results show that when comparing 1A and 1B, the utilization of waste heat reduced the plant avoided cost with close to 30 euro per ton, but the costs are still high. An increase in CO2 concentration reduces the cost with an additional 30 euro per ton, and as expected, capturing CO2 from a larger plant is more cost efficient, as it benefits from economy of size. So looking at the operational cost in detail, it can be observed that maintenance and personnel costs contribute disproportionately for the small plant. And regardless of plant size, we have included 1 operator per shift and 1 engineer is included. So the second plant investigated was a generic plant, but it is representative for ferrosilicon plants in Norway. It has 2 furnaces and produces ferrosilicon primarily for the iron and steel industry. The annual CO2 emission is about 250 kiloton, and for this plant, furnace off-gas recycling is being explored. The production plant is very similar to REC Solar. In addition to carbon and quartz, iron is also supplied to the furnace. The other difference is that a share of the off-gas leaving the filter is recycled back to the furnace. A traditional off-gas leaves the filter at 4.4 volume percent CO2. Off-gas recycling can increase the concentration to 15 volume percent, and in the case of 2 furnaces where one is operating as normal and one has recycling, a concentration of 6.8 volume percent is achieved. As no excess heat recovery is assumed installed, it is sufficient excess energy to recover 90% of the CO2. For the generic plant, the effect of off-gas recycling was the basis. However, the feasibility and cost of modifying the plant has not been considered. And there are 3 scenarios: 3A, 4.4 volume percent, 3B, 15 volume percent, and 3C, 6.8 volume percent. And all scenarios utilize waste heat. The figure shows that the plant avoided cost is reduced to an increased CO2 concentration as expected. It can also be seen that cost of capture is significantly lower than for REC Solar. As there was sufficient excess energy to capture 90% of the generated CO2, there was no obvious scenarios for partial capture. However, as there are plants that do recover excess heat today, partial capture scenarios involving seasonal capture was developed for REC Solar. The main assumptions here were that waste heat for district heating is only sold during the winter months, that means 6 months of the year, that the waste heat can be used free of charge for CO2 capture during the summer months. Full-size capture plant is built with a capacity to capture 90% of the CO2 produced at any given time. The value of the steam as district heating was set to 16.7 euro per ton. This is an important assumption, but is also a very uncertain one. All year capture includes a loss of revenue from sales of district heating during winter. The results show that with the current assumptions, seasonal capture is more costly than all-year capture. It can also be observed that the seasonal capture results in change from OPEX to CAPEX as the main contributor to the cost. Okay. So, final remarks. It's clear that the overall conclusion is to utilize excess energy for CO2 capture. For REC Solar, the main findings are that the low CO2 concentration and small source make CO2 capture costly. A relatively small increase in CO2 concentration to 4 volume percent is beneficial as expected, and the same is found for increased plant size. For the larger generic plant, increasing the concentration is beneficial in regard to cost. The reduction in cost, however, needs to be weighed against the changes needed in the process. Higher concentrations may also make other capture technologies attractive. And finally, for the seasonal partial capture, the findings show that it could, under the right circumstances, be considered, and the results are highly dependent on the value of district heating. A further investigation into the possibility of combining heat for CO2 capture and district heating is recommended, and it should also be assessed for plants larger in size and or with a higher CO2 concentration. And with that, I leave you to Jens Wolf.
Thank you, Annette. My name is Jens Wolf, and I'm going to present you the results from the pulp and paper case. Let's see if the same problem as you, Annette. No, it changes. But the difference from this case to the other cases is that the pulp mill actually is already almost climate neutral. The pulp mill receives biomass from the forest and produces products, and the emitted CO2 is then recaptured by the growing forest. Here it's important to remember that the growing forest is absorbing CO2 and not the aging forest, which is more or less in balance. And this means that the pulp mill actually makes climate neutral packaging. Then applying bioenergy, carbon capture and sequestration, this is so-called BECCS in a pulp mill, means we actually make a climate positive packaging since the overall CO2 emission is negative. Parts of the CO2 is captured, and the returning CO2 to the atmosphere is less than the amount of CO2 that is captured by the forest. So in Sweden there's quite large potential for this since pulp and paper industry emits about 22 million tons of CO2 each year, which potentially could be captured. But where comes the energy from to do this? Carbon capture is an energy-intensive process, as we all know, and at the pulp mill there is no waste heat or no free energy available. Mostly northern pulp mills have some waste heat available in form of hot water at a temperature just below 75 degrees, and they have a lot of hot water available at temperatures below 60 degrees. But in this study we looked at the MEA absorption process, and then we need a heat source which has a temperature above 100 degrees and preferably 110 to 120 degrees. So this means we need low pressure steam to recover our solvents, and there we have basically two possible energy sources in Sweden. And that one is the climate neutral power from the Swedish power mix, which could be used in other processes basically that we looked at here, the hot potassium carbonate process, which needs a higher pressure, or a membrane process. But in our process we need heat and steam. So the preferred source for energy would be using more biomass or waste with at least some caloric value, things that can burn to produce steam. And that would mean we need to feed more biomass into our pulp mill, and by that also produce more CO2 that would be released into the atmosphere, and then hopefully be recovered or recaptured by the forest. Here it's important to notice that the CO2 that would be in addition emitted due to an extra combustion unit is much less in absolute numbers than the CO2 that is captured and sequestrated in a geologic storage. So even if it is necessary to burn more biomass to capture CO2, this concept makes sense. In a pulp mill, we have basically three sources of CO2. The largest one by far is the recovery boiler, and then we have the lime kiln, which is used to recover the calcium oxide, which is needed in the pulping process, or to recover the chemicals, the pulping chemicals. And the third one is a power boiler, also called bark boiler sometimes, since it utilizes the byproduct bark to generate additional process steam. In this study we used a modern standalone kraft pulp mill as a reference mill, and this is standalone in this case means that we don't have a paper machine or a paperboard machine or a carton machine included, but only a pulp dryer. And a pulp dryer consumes much less steam than a paperboard machine, and for this reason, it is usually the case that we have excess steam, low pressure steam available, but any pulp mill who has low pressure steam available will do something with it, and one standard possibility is to use a condensing steam turbine to generate additional green electricity to become more independent of electricity supply from the grid, and or to actually sell electricity. In our case, which is a fictive case, a fictive generic reference plant, since we don't had a pulp industry partner involved in this project. So we have a generic one, and in this one we have a quite large steam turbine and a quite large condensing turbine, since the process is very efficient, or the pulp mill is very efficient, and we generate green electricity and also receive green certificates in Sweden. So our cost our cost for steam would be the lost energy, the lost electricity that we cannot sell, since we make CCS instead of electricity. I explain this more in this slide. So we defined 4 cases, and in 5 cases, and in each of the cases, low LP steam at the pressure of 4.5 bar is taken from the LP network in the pulp mill and used in the reboiler of the CC plant instead of the condensing steam turbine. And as a result, we lose income from salt green electricity. In cases where the steam requirement was larger than that available, by even totally disconnecting the condensing steam turbine, we added a new bark boiler. Now we calculated a lot of cases, but I picked only 5 to show here, and the first one is capturing of 95% as a so-called full capture case of only the lime kiln. The second one is only capturing from the recovery boiler, but here we maximize the amount of capturing CO2 if we disconnect the condensing turbine totally. We further increased the capture rate of the recovery boiler up to 90%, which would be a full capture case of the recovery boiler, and for this we need additional energy, so we included a new bark boiler. The last case here would be to have a full capture case both from the lime kiln and the recovery boiler, and that also includes a new bark boiler, which is of course much larger than the one in this case. And then in between we have case 4A, there we didn't invest in a new bark boiler, only disconnected the condensing steam turbine completely and used all the steam to capture 95% from the lime kiln, and then as much as possible from the recovery boiler. We have to admit here that in cost cap we only cover a smaller share of the Swedish pulp and paper industry, since we just, as I just said, we chose the standalone pulp mill. And in Sweden, the most pulp mills are integrated, which means the costs we calculated in this project are a little bit tricky to extrapolate to all the 22 million tons of CO2 that are in principle available, since we looked at a standalone pulp mill which has cheaper steam available. This comes from the fact that the cheapest steam is available when we disconnect the condensing turbine, and more expensive steam can be made available by investing in a new combustion unit. The results from the techno-economic study are illustrated here. On the left-hand side, we have the CO2, the cost of CO2 capture, so euro per ton captured CO2, that would be the staples. The light green part is the capex, and the dark green part is opex. And on the right hand side, connected to the red dots, we have kiloton of CO2 captured per year. As you can see, the best results we got, or the lowest capture cost we got for a maximum partial capture. It is in principle what Max showed before. We maximize the possibility to utilize the economy of size, and we had to add a new boiler if we increased the capture, and then we needed to handle this higher investment and the relatively high cost of biofuel in Sweden compared to the relatively cheap electricity in Sweden. So here we have steam cost based on almost only electricity that we don't have salt, and here we have steam cost based on electricity that we don't have salt, plus capex of a new boiler, plus the cost of biomass that has to be bought on the market. And as I said, what I already said before, we have to be careful to extrapolate the results from this fictive plant that we studied, since it is a standalone plant and most of the plants are not. So we cannot disconnect the turbine. That means we have, relatively speaking, to invest in a larger bark boiler, and in this study is not included the intermediate storage at the Haber, which is necessary, and in many cases the Haber is a few hundred meters or a kilometer away, so a pipeline has to be made available to the Haber as well. These kind of things are not included, and I have not calculated this black staple, but it is probably not less than additionally 15 to 20 euros per CO2 captures. And then, of course, the transportation by ship and sequestration under the North Sea is not included either. Conclusions. The Swedish pulp and paper industry has the potential to capture about 20 million ton biogenic CO2. Okay, that means that much CO2 is emitted, and so in principle it could be captured at this higher cost I showed, but it's not necessarily economically interesting to take it all. As a result of our study, we found that in partial capture we could get a cost of about 40 euros per ton, and if we need to invest in a new boiler, the cost increases, and in our case the maximum was about 60 euros per ton. But this has been the fictive plant, and in reality, or in the northern countries, the most plants do not have a condensing turbine that can be disconnected. So we believe that the last or a major part of this 20 million ton actually may be between 70 and 80 euros per ton CO2. This is still relatively low, also if you compare this to the silicon case you saw before, since the concentration of CO2 is quite high in the flue gases, and we have large point sources. The disadvantage is that we don't have any waste energy in pulp and paper industry that we can use without heat pumps or other tricks. So that is a disadvantage. An advantage again is that we have an existing infrastructure for fuel ashes and usually nearby Haber. However, this is BECCS, negative CO2 emissions, and this is not included in any of the economic systems that have been introduced to push CO2 capture. like the ETS in Europe. So we have no or few incentives for CO2 capture, and this requires this concept to be implemented requires new financial measures to stimulate investments. Yes, thank you. And now, should I give the presentation back to somebody, or should we?
I can switch it back, Jens. Hold on 1 second.
Okay.
Oh. Okay.
Okay, great. So thank you all the speakers, and thank you Jens for transferring. We have time for a few questions, so I'm gonna go through a few questions from the audience, and I will give the time for the speakers to answer to them. So first, I would like to give to ask actually Ragnhild about the energy scenarios that were included. One of the listeners was interested in knowing how it influenced the results.
The steam cost?
Energy scenarios included in your analysis?
The energy scenarios?
Uh-huh.
That's
the question, yeah.
I'm not sure if I quite understand how that what they are asking for.
Yeah, it's possible that maybe the listener was referring to energy recovery and how it was integrated, and how do you think it can impact on the results?
Yeah. Okay. So yeah, it will impact on the result, because the waste energy that available, we took and estimated the cost for that, and that was part of the operational cost. So if they had energy available, it reduces the operational cost for the different cases.
Yeah. Okay. Yeah, that's interesting. This impact.
Yes.
Yeah. So then maybe we can jump to the second question. So that is actually related, but is directed to Max. So the listener was wondering how the steam cost was assessed in terms of how it was included.
Yeah, that's a good question. Well, I'll answer it from the steel perspective I've been working on. I've been working together on that actual question with Hassan Ali from USN, and we've been considering capex as well as opex for the steam cost itself. So we included steam piping to the reboiler. We've included heat retrieving equipment such as heat exchangers, steam boilers, condensate pumps, condensate buffer tanks. And then we also accounted for OPEX, so electricity costs for driving those pumps, cooling water costs, and also maintenance. So we try to really assess what is the cost of bringing the steam from, let's say, some point in the steel mill where the heat is, to convert it into steel and to transport it via ducting to the reboiler. So we try to include also the locations, of course, for the reboiler compared to the heat source. So that was kind of essential.
Okay, great. Thank you for your answer. Maybe related to that, also there was another question about how the district heating delivery from the steel mill CHP was affected by the CCS.
Yeah, that's a good question. Since the temperature levels are maybe perhaps similar, or at least district heating is maybe below 100 degrees and MEA is above, but still that could be an interference. We didn't touch the heat delivered to the municipality in our case and the steel case, but the relation between the amount of heat and the quality available from the industrial CHP to cover both the district heating and the CCS is something we started looking at. And we see the potential for CCS, especially during the summer months, something Annette was talking about. But we need to investigate this further, what actual implications this has for cost also in the steel case. Yeah.
Okay, great, thank you. So the next question will be directed to Annette. And the listener was wondering, which are the challenges do you consider in this industry?
Well, yeah, like the presentation shown, we had looked at two different plants. The first one, a really small one with just 1 volume percent CO2. We probably wouldn't recommend to start there. But the other ones with for ferrosilicon, where there are quite a few of in Norway, there's definitely a potential, even at 4 volume percent. And if they manage to succeed with the recycling of the flue gas, because there are some changes needed to the process, but they think it's definitely doable. So there is a potential there to have a higher CO2 concentration, which may again open up for other capture technologies other than just chemical absorbents.
Okay, great. Yeah, thank you for your answer. And there are a couple of questions for Jens about his presentation. And one of the listeners was wondering, what is the CO2 concentration in the flue gas?
About 20 weight percentage.
Okay. Okay, great.
Like,
Yeah,
like in a combustion plant of biomass fired CHP plant, or also coal-fired power plant. It's not that different. In the lime kiln, it has the potential to be significantly higher, but in reality, lime kilns at pulp mills are not optimized to produce high CO2 concentrations. Actually, in many cases, the flue gas is used to pre-dry the lime that is coming in, and by that it is diluted first by steam and false air entering the system. And in addition, the secondary air intake is not either optimized for this, so it's a quite high oxygen in concentration, which may actually lead to severe problems in MEA process. Things have to be done by lime care properly if the MEA process should be used. So that makes actually the recovery boiler a little bit more interesting from the flue gas concentration point of view.
Okay, great, thank you. And one second question for you. Someone was interested about the potential for BECCS in Sweden. Do you know how many tons of AGEA could be captured?
Yeah, as I said, in the pulp and paper industry, it was 2070 at 22 million tons a year. But that means, of course, all of it, and it is the more we want to capture, the more costly it is, and the cheapest one may be able to be captured 40, and then the highest one would be up to 80, as I speculated a bit there. Then we have about 10 million tons from biomass-fired CHP plants. The biggest one is in Stockholm, at Stockholm Exergi. So it's about 30 million tons a year, which is actually, when you compare this to the CO2 emission, the fossil CO2 emission from the transportation sector, so that is also about 20 million tons. So in principle, you could offset all of that.
Okay, great. Thank you for your answer. So we don't have much time for more questions, but the speakers will try to come back to you later by email. And I would like to thank you everybody for attending this IGG webinar. I really hope that you enjoy. And I would like to remind you that we will have the 5th Post-Combustion Capture Conference in September in Kyoto, Japan, and the early bird registration is valid until next Monday. With that, I would like to thank all the speakers and my colleague Susan, and you will find the report of the COST Cap project in their website soon. And also this webinar will be recorded and will be available in YouTube. said that, I would like to close this IGG webinar. I would like to wish you a good rest of the day, and I hope I will see you all soon. Bye, everybody.
Goodbye.
Bye.
Bye.